You continue to fly along in the integration world, and we're about to learn your last new technique of your BC career. Someday this might be waiting for you, but we're going to talk about improper integration right now. And it is improper, but I promise you we won't tell your grandma or even your parents, so you can feel safe doing it. And let's talk a little bit about examples of why you would ever need improper integration. First of all, these two stick out very obviously to you. Right away, maybe, hopefully, you would notice that you have something unusual going on in the limits of integration. We have an infinity. What the heck? So that's a good clue that you have improper integration. These two down here aren't as noticeable. In fact, they look pretty docile at first. But this limit of integration is a 0. And if I think about this function 1 over square root of x, it's not allowed to exist when x equals 0. So this 0, this causes this integrand to blow up, which causes us to use improper integration. And then if I look at this last example, neither of these limits of integration blow up this integrand. However, if I think about what would blow up this integrand, which is an x equals -1, -1 falls within the range or the interval of my limits of integration. So these two require improper integration because one of the limit values or something within there blows up the integrand, makes the integrand undefined if you want to be picky. And then over here, how in the heck are we going to deal with infinity in the limits of integration? So that's a good clue on how you would spot this situation. I would like to remind you that I'm getting these examples out of the notes packet that's provided for you on the lesson plans, and it's completed as well. This notes packet goes a little bit more in depth, so you probably do want to take the time to take a look at that. All right, let's get back over to this improper integration, and I'm going to focus in the beginning on these two problems with infinity. In each of these cases, I'm asked to do something mathematically uncomfortable. Let's start with this one over here, 1 over x, because it's using positive limits of integration, and that's a little bit easier to comprehend. But the graph of 1 over x looks like this. And the integral is asking, hey, can you give me a number for how much area is trapped between this graph and the x-axis? In other words, how much area am I filling in right here? Well, we have a problem though. This area continues on forever and ever and ever, but also this graph is getting closer and closer and closer to the x-axis but never touches. That's weird. So how can I come up with a number for that amount of area if it goes on forever? Or is the answer infinity? Maybe it's infinity. Maybe the answer is a number because it seems like they want us to get a number. Well, I don't know. That's why we're going to use improper integration. The same idea is happening over here. 1 over x to the 4th looks like this. If I go from -infinity to -2, I want this area, and same dilemma, that region goes on forever because I'm going to -infinity, but it's getting smaller and smaller and smaller. The only way to solve this, improper integration. Or stick around till later in the year when we learn about sequence and series as well. That's going to be very exciting. So now we go from the daydreaming of that dilemma to the nuts and bolts, the nitty-gritty, the math steps. As you recall, we have that dilemma. How much area is trapped underneath there? Is it infinite? It seems like it because it goes on forever. Well, when I have improper integration, I'm always going to have a limit. A limit is going to be in our integral. And you need to write that limit. The problem is students rebel against that and they don't feel like writing it. And every time you go to a new step, it's still a limit problem, so you still need to write that. I wish I remembered how the AP catches students who don't write that, because there was a tricky question that got you if you weren't writing that. But anyway, that's not for right now anyway. I take this example, and now I've done an eyeball adjustment. I've called this x to the -4 in the numerator so I can do power rule. But what I've done is I've taken this negative infinity and called it an a. That's one step better than negative infinity because we've dealt with letters in our integrals before. But now I'm just saying, hey, that a, we're going to pretend that we're in a limit problem where a is approaching negative infinity. So it's kind of like a cheesy, lawyer-like substitution. Get rid of that negative infinity, give me a letter, but oh yeah, we're still approaching that negative infinity. Now, as long as I'm willing to just recopy that, life is good. I do the same thing I normally do. I do the antiderivative, and there's the limits of integration. I go to the next step. Notice that I'm still writing that it's a limit. And this thing, I rewrote like that, so it's easier to plug in. I go to the next step, and now I've plugged in my -2, and I've plugged in my a. There's some trickiness going on with the negatives there, but really we've just plugged in the limits of integration and subtracted. So now things are starting to spice up a bit in a good way. Some maybe cinnamon and nutmeg and cloves. Oh, so good in a cookie. As a approaches negative infinity, this is unaffected because notice this doesn't have any a in it. So this really ignores that, and this just becomes 1/24. This term has an a in it, so this limit is definitely affecting that. Minus a minus is a plus, and now I have this limit problem. This should be a pretty reasonable limit problem. As a approaches negative infinity, my denominator is getting huger and huger and huger. 1 divided by huger, huger, and huger is a 0. So this whole thing works its way towards 0. Hey, we came up with an answer. Not only did we come up with an answer, but that answer is a number. It's 1/24. That means this region that was going on for infinity only adds up to the number 1/24. It doesn't add up to infinity. That's freaky, isn't it? We're going to learn more about that with sequence and series. So if this area from this problem was 1/24, that's actually surprisingly small too, isn't it? This area you would think would end up being a number, but it's not. This area is going to end up being infinity. What the heck? How can that be? Well, we're going to show you using improper integration. So for this one, I'm going to go back to the note packet. I'm not going to work this one out step by step separately. But we take the original integral problem and we say, okay, I have an infinity up there. That makes me feel uncomfortable, so I'm going to replace it with a b. But I still have to basically accept that I'm approaching infinity. So if b is approaching infinity, that's good enough. I take this problem, antiderivative. It's still a limit problem, so I'm still writing limit. And I plug in the limits of integration and I subtract. It's still a limit problem. When I do that, the natural log of 1 is 0. I should know that because I'm a math student and I know what the graph of natural log looks like. But now as b approaches infinity, what's happening to the natural log of b? Well, if I think of what the graph of natural log looks like, it's looking like that. As I head out to infinity, the natural log is also going up to infinity at a very slow rate, but it is. So that piece ends up being infinity. Thus, the answer to this integral is not a number like the previous one, it's infinity. So you probably can't just trust your gut instinct. You're going to have to do the math to find out if an improper integral is an actual defined number value or if it's an infinite value. So we ended up with equals infinity for that. And by the way, that would be called a divergent integral because we didn't come up with an exact value. I believe this one was 1/24th, and that would be called a convergent integral because we have ended up with a defined, definitive number answer. Okay, those vocabulary terms are going to come back to us with sequence and series problems later on. But now I want to point out what happens with these two, and these two are when the limits of integration wreak havoc in the integrand, most often the denominator of the integrand. In the problem that we have up here, we had determined that the 0 causes a problem in the denominator of the integrand. So the 0 is the problem child here. It makes us uncomfortable, so we replace the 0 with an a, but we must still acknowledge that that's really approaching 0, so this limit notation says, see that a? It's really approaching 0, but now I feel more comfortable. And from here, your steps are the same. Antiderivative with limits of integration, it's still a limit problem. Plug in your limits of integration, it's still a limit problem. Now as a approaches 0, the 2 square root of 1 is unaffected, so that remains a 2. As a approaches 0, this is a plug-in. I don't even have to do much limit calculation. Plugging in a 0 means 2 times the square root of 0, which is 0. So that answer is 2. Even though the 0 blows up the denominator, or the integrand itself, the amount of trapped area is still 2. Let's take a look at this final one, and the math gets very messy at the end, but what's more important is the original setup. So in this problem, if you recall, going from -2 to 3 for our interval, our domain for our limits of integration, caused us to go through a -1, which blows up the denominator. So what I'm going to do is think about it this way. What if I went from -2 to -1, and then from -1 to 3? Now I have kind of exposed the problem child. Well, if that's the problem child, replace it with a letter and make it a limit problem. If that's the problem child, replace it with letter and make it a limit problem. Now when I do the antiderivative, limits of integration, still a limit problem. Antiderivative, limits of integration, still a limit problem. Now I can plug in my limits and subtract. It's still a limit problem. Now, as I go through that, this is where my work got messy and is definitely a math black hole. But as I start plugging in this, as I start plugging in this, I'll end up with these mysterious values of -infinity and +infinity. If you can plow through all that, you end up with natural log of 4, which is a number, so we would call this a convergent integral. This part might be bugging you. The part that you need to make sure that you have installed in your brain is how I went from here to here to here. Because once we're to here, it should just be your standard normal integration. I just happened to select a problem that got really, really messy. We've done it. We've gotten through the 3 new techniques, or 3+ new techniques, and you'll have noticed that to do these, we had to be pretty good at that. This could even show up, and someday. So please practice, because getting these techniques down really seems to only work with a little bit of practice or a lot bit of practice, and students fall victim to that. You're done.